Sweet. All right. So we talked a little bit about memory and stuff 2 weeks ago, just the basic read-only memory, right? And that was kind of neat, just because we kind of started figuring out how to represent instructions, but for the first time, instructions that we could quote unquote read. Um, and that's exciting just because this is something that we haven't really explored in like other CS classes, and I feel like that's kind of when we start bridging the gap between the CS classes that you've kind of taken already, right? Um, and the sort of lower level stuff that we're working on here. So we're almost coming up to nearly meet where 216 kind of ends its specificity, right? I would like to say that 216 goes all the way down to assembly and then kind of drops off. And then we try to go from the opposite direction. We try to start from like the very basics and go all the way up to assembly and meet them there. So I feel like kind of learning all of it lets you experience the whole stack um, of digital systems that kind of make up this whole computer architecture stuff. So obviously more covered in like classes like 411, but it's a neat way to kind of start building your background knowledge of this sort of stuff. So we're going to expand upon this memory of idea this week, just because although we did kind of come up with a way to store items, memory, right, last week, we can't really say that it was optimal. Our biggest issue is, if anybody can remember, well, it was 2 weeks ago. If anybody can remember, the biggest issue, it really was that we'd have to go in and change the torches, right? Change the torches to make sure that our memory changed. Does anybody have any questions about that, by the way? Because I'm happy to answer them. It's good to remember that stuff when you start off with this lecture. So if anybody needs any, yeah, I'm on lecture questions. So if anybody needs any clarification on that, it's that we were able to store data last time, but unfortunately we had to go in and manually edit that ourselves should we want that to change, right? In other words, we had a bunch of torches set up in a specific layout, but if we wanted to change what that memory was, we'd have to go in ourselves and change it. So again, pretty akin to the name there, read-only memory. Um, so obviously that's neat and that's exciting, but at the end of the day, it is read-only, right? And we want a way not just to read from memory like we did, but to digitally change that memory. In other words, change its state from perhaps on to off and off to on. So let's kind of start investigating how we could do something like that. Well, I'll kind of just skip over the announcements bit here. This is just stuff from last semester. And this is when we invented the Discord. And all of, okay, well, yes, there we go. Sequential logic. Now, to understand sequential logic in the first place, we have to make note of what we know about a combinational circuit, right? And in other words, what we've already done so far is kind of just been like very simple stuff, right? So remember when I was earlier talking about iterative algorithms and how you have to perform operations over and over again and store that data and come out of it? We're kind of sort of getting there now, right? So combinational logic basically relies on only the inputs, the initial inputs to make a decision and come out. So in other words, you've had like a set truth table for your combinational circuits. Knowing the inputs that you give in will always provide certain outputs. And if you're wondering, some good examples of these are just adders, full adders, half adders, very simple stuff, right? So I've got a little diagram here that shows just you have these defined inputs, a combinational circuit, and the expected outputs for those. Um, and that's basically it, right? No need to kind of take into account what the initial state of the circuit on the inside may be. No need to take into account anything else, right? And that's kind of what we're getting at there. The reason I bring this up is because once we start working with memory that can be changed, this sort of stuff is different, right? Suppose you had some sort of conditional memory within your circuit, right? And you didn't know if that conditional memory was on or off, and that could change the output of your circuit. That's when we start thinking about some more advanced ways to handle circuits. So the reason I kind of bring this up, just to give us an introduction, is the whole point of a circuit like this is not knowing in one cycle what your output is, right? In other words, these circuits, they don't just use the initial inputs, they use the outputs of previous iterations of the circuit to decide the output. And this is kind of an interesting idea, just because I feel like it's the basis for understanding, loops and recursion when you start building this up in terms of computer science knowledge, right? So you can see in this diagram that I've made here that if you almost want to think about it in a computer science sense, right? We've got inputs and we've got outputs and we've got our circuit, and we're used to seeing stuff like that. But I also have this additional variable here called state. Um, and it's neat to think about it in the context of perhaps like recursion or loops, right? Where you have circuits producing output that goes ahead and gets stored at state, and goes ahead and gets re-inputted into the circuit and is used to perform the next calculation, right? So one cool example of this would be perhaps a counter, right? Perhaps your circuit represents binary numbers, right? And then every time you activate, I don't know, you run some inputs into the circuit, that binary counter would go up, right? Again, I'm kind of giving that example for a specific reason, just because that basically is a program counter, and we'll be working on something like that. But think of it that way, right? It's a great construct to think about in terms of just computer architecture and figuring out this stuff with memory. So, how do we achieve this? Um, yeah, we're basically just doing what the diagram says, feeding the outputs of our circuit back into our circuit for further processing, right? So again, I say right here, if you want a programming analogy, think of a loop statement with a loop variable, right? Um, right here, I have iterative code, but it's just about the same to consider, right? My input variable equals 0, and then, this is Python, by the way, right here. Um, and then we just have a range here from 0 to 10, and we keep incrementing that input variable, right? And if we go back a slide, that's kind of what's going on here, right? We have some inputs, right? And, who's to say that one of these inputs does not store that value in state, right? So that'll come in, establish the primary value of state, and then, state can go over and over again and change what's going on in there. So that's kind of just a cool thing to think about, right? And the reason I kind of get us started on this train of thought is that once we start working with memory, this idea of circuits not just being represented by a very simple truth table is kind of what's going to bridge the gap for us, right? So really kind of think about that, because previously we were just building stuff that took some inputs in and threw out an output, right? Calculators, addition, subtraction, that sort of stuff. It's great, it's excellent, but we're going to need to expand our ideas just slightly more if we're going to go to some real like computer architecture, right? And the idea of sequential logic, right, is kind of paramount to that. So this is like the most simplified way of looking at it. But I have a feeling that when we start getting into some more memory examples, this will become a lot more clear. So that Python segment may have made sense in our heads, but we're missing a key element to help us translate this into digital logic, right? So again, let's take a look at this Python statement. Right here, we're keeping track of a variable as we continue in that loop, right? So I want you to pay attention to state, because this is our main idea here. We're gonna have to start thinking about how we're actually gonna deal with this guy. So when we go over here, we have no idea how to recurrently store the value of a variable every time our circuit executes. This is correct. If you think of all the circuits that we've made already, right, we really have no way of storing some value of data, whether it could even be a Boolean flag. We have no way of storing whether something should stay on or stay off. And the key there is that we can't provide that answer um, without power flowing through like a certain point in that circuit consistently, right? Because you might think, oh, once I've set something to when something is off on my circuit, right? It's just inverting an on signal. I guess that's storing something. But the key you're thinking about there, if you think about an example like that, is it's always going to have input energy in order to function as it is. If you cut off input energy to just a NOT gate, it's going to become the output will become positive. So what I'm trying to say is every single construct that we have now, if you cut off energy to it, it's not going to be able to store what its state was. It just doesn't have the ability, right? The closest that we have to that is the torches that we put down to represent memory. But again, our big problem with that is that we can't edit that. So whatever it is, whatever the case is, we either cannot change the state that we've got built into our circuit right now, or even better, we can't even set it ourselves, right? So our goal is to build a construct that can store some data, right? Whatever the case is, we can set that memory. So I know right here I mentioned we're looping back to the idea of memory. Oh, well, okay, that's just a pun. That's fine. I had a lot of puns in JoJo references last semester. Cut down on those. Right. So that's where the idea of latches comes in, right? I feel like this is kind of the key, what we're getting at here. This entire lecture, I have some drawing things set up, so hopefully that might make this a little bit easier to understand. So we'll try that out when we get to the diagram. But that's how we'll address this problem, right? We need a way to store memory. So we use this construct, called latches. This was a big problem before. People had no idea how to solve it. Engineers came together and produced this idea. So let's go ahead and investigate it ourselves. Right. The first ever type of real memory, right? And I'm not talking about read-only memory. I'm talking about persistent memory in a computer was a chain NOT gate, right? Um, and go ahead and try to imagine what would happen to the output if the input was 1 or 0, right? And keep in mind that it's important to consider the output state before this. So let's think of it this way. Here's my, let's test this out. Let's see if this works. Okay, so make this a little thicker. All right, so assume that we have this circuit right here, right? And it's all black right now, and let's think of black as off. So in this state, input is 0, right? And output is also 0. Our circuit is saying, oh, yeah, you got nothing going on, and obviously since nothing's going on over here, nothing is being shown in output. However, once we turn our input to 1, let's follow the path of the redstone current, if we will, right? So we start off with electricity coming in here. That's fine. That's all good. And then at this junction, you'll notice some neat stuff, right? So we'll follow one path of it first, and then I'll explain kind of why we have these NOT gates here. Electricity goes this way, through the NOT gate, inverted, right? That's fine. And you'll notice that this right here, this kind of keeps it going, right? Flips it. Kind of comes around here, and then maintains persistence here, right? And our key is to kind of imagine what would happen if the input was 1 or 0, because right now when we have a current flowing through here, right, the output stays at 0 until the input becomes a 1. Then, no matter what this input changes back to, the output will still stay at 1, right? Oh, and by the way, I forgot to mention at the beginning, at the outset, right? So I should probably go over this bit, just so it doesn't become confusing. I just realized before the circuit does anything at all, right? Let's talk about that. Before the circuit does anything at all, it's coming in as a 0, and this right here, this is on. This is a key bit to remember. This is on. Hopefully everybody understands why that is. 0 coming in here, NOT gate flips it, that comes out to 1, and then the NOT gate flips it again. So this is our first state of the circuit, right? So input is 0 and output is also 0. Then we have the privilege of being able to put in an input right here. So now this is our default state, right? So keep that in mind. So then we put an input here, and it'll go like that, continue this way, go to that NOT gate. Again, nothing comes out here. Over here, we have electricity come out. It'll loop back around. That's good. That's fine. We kind of need that. So it'll come back around this way, and it'll also go out this way, right? You might be thinking, why exactly was something like this necessary? Well, let me tell you, for a few reasons, right? And the main reason is the whole magic here is that when we stop providing input here, when we stop providing this in signal, we've still got like a short circuit loop, right? This closed loop will continue sending redstone in a circle like this. So in other words, we have essentially activated this memory, right? Once we send this little block right here, we send it one little in signal, it'll say, oh, I've got one. Now I'm just going to hold on to it for the entire time, right? I'm going to keep going, keep circulating it around. And of course, some people might say, okay, well, why don't you just, just make this loop, right, without the NOT gates? And that's for a few reasons, right? Number one, though, I would say is to prevent, backflow. We've got this right here, and we want to make sure that the circuit only works if we're pulling in stuff from the left side input, right? These NOT gates also act as diodes. So I see perhaps some questions are being produced. Let's talk about those. Same thing as read-only memory. Excellent, astute point, right? Exactly. You can't change it. That's how we're starting off. The cool part is, though, technically we can, right? And Daniel, the reason I say that is because when we have this stuff going on, right? Keep in mind, the initial state of the circuit, wouldn't one for the input also send a current up and to the right? Yeah. So that's the thing up into the right. Okay. So you have input here, and it sends current up into the right. Um, no one for the also sent. Is there a diode or something to the right? By up and to the right, do you mean like through this way and then that way and going out?
Yeah, I think he's saying like we didn't make it clear that the which way the current flows in this instance. It can't go
Oh,
up
yes.
that wire.
Mm, yeah. That's a solid point. Um, Incidentally, I feel like it doesn't even matter though in this case, just because when you provide that in, right? You're going to have red come out this side either way, whether it interacts with this double knot or not. It'll continue um, that way. So in other words, I don't think it really needs to even matter here. When you have a one coming in, it'll go this way, and then it'll do the whole loopy thing. But it'll also go this way and come back out, and that's fine for our purposes. Um,
In regards to Minecraft, you would just slap a repeater on like the first intersection, like where
mhm,
in splits, so that the current can't flow up because repeaters act as diodes in that sense.
mhm. You could totally do that. In this particular, so the reason, I mean, this is more of a kind of theoretical example that we're going to build off of to produce the actual memory. Minecraft is yep. In the real world, it's kind of the same thing, right? Electricity flows always. We just put in diodes to make sure it flows in certain directions. Um, but again, I want to emphasize that in this case, when you have input coming in here, we want this output to be red. We want that out to be red, right? So we don't really care whether it comes from here or from here. For the purpose of this particular circuit, it doesn't really matter, but that's a good eye, right? We'll kind of build off of this idea, and we're going to need to modulate the flow when we get to our more advanced kind of memory construct. But great point, and exactly, diodes is redstone repeaters. Cool. So Daniel's mentioned. I want to get back to that question. Isn't this the same thing as read-only memory? You can't change it, and that's exactly right, right? That's the first bit there. But keep in mind, we are doing one more thing than read-only memory. For read-only memory, you just had one torch sitting there, and that produced a constant flow. That goes off into nowhere. Great, a constant flow of electricity, right? Um, and that was bad for us because we couldn't really change what the input was. Here we have a bit of an opportunity. Here we start off with absolutely nothing, right? Um, so we can, if we need like a single use sort of thing, right? If we need a circuit that can start off like this, why isn't that going away? That is so weird. Eh. Okay, well, slightly jank. Um, we start off like this, right? With nothing coming in the output. Then we can opt to make the decision to turn on this flag forever, right? So we've basically invented something where we can turn it on if we want to. So it starts off as off, and then we can turn it on at some point. Extra credit quiz is live. Hashwat just threw it up on the elms, so feel free to knock that out whenever. But Daniels, I hope this kind of makes a distinction for you. Does that make sense? Right? Now we have something that starts off as off, and then we can turn it on whenever. And of course, it'll stay on, and that's kind of our problem now. But we've kind of built in a new functionality. So does that make sense? Maybe. Oh, okay, cool. Yep, all good. All right. So again, this is just kind of an idea that we're going to build off of, right? This is just the initial bit, the initial start of it, right? So again, this is the previous state, and then when we turn everything on, we'll just go whoop. And again, just like Brian mentioned, I'll do this for the sake of keeping that example good as well. So this happens, this goes out, and that's fine, but that's not really our concern, because our real concern is what happens when we cut off the power here, right? When we cut off the power here, no matter how the electricity traveled through in the first place, we now have a very consistent circuit, right? That has a short circuit built in, just like this. Flips in the middle here twice, and again, this is diodes, right? This basically says that it serves a double purpose. These two knots say, okay, well, nothing can go backwards through both of us. So electricity kind of only flows that way. It's just a neat way of keeping track of that, right? So whatever happens, backwash will be eventually prevented. But this is the final state of the circuit, right? Once we give it one little zap from the in, it'll just keep sending red on the out. So in other words, we basically turned a flag from 0 to 1 permanently, which is better than last time, right? With read-only memory, we had a flag set to whatever we put it down in terms of torches. Now we can turn something from 0 to 1, and then we're kind of stuck. We don't really know what to do from there. So we've kind of half built, like half-assed some memory here, um, and this is kind of a stepping stone on building actual memory, because it turns out this is the right idea, right? We want to keep track of something using a weird little form of a short circuit like this, right? So keeping that in mind, let me disable this draw tool. Keeping that in mind, let us move on to the next, like sort of the next iterative build of this idea, right? So we want to do something more than that. We want to set the value of memory more than just once. And I'm going to go ahead and introduce some terminology here that'll kind of move us along, but you could also say that not only do we want to be able to set it, right? So over here, we would consider us feeding in input like that, and then eventually getting read as output. So again, I'm not going to draw the whole thing, but we would consider that setting that memory, right? Because once we give it one little zap on this side, this thing gets set. The output goes, oh, yep, I'm good to go. I will always be producing that, right? So we're setting that memory. Um, oh, cock. There we go. Um, Once we set that memory, though, we also want to reset it. In other words, we want to say, okay, once I've set you, I also want to throw in perhaps another signal, right? And then I want you to flip back to 0. Fortunately, this is impossible with this circuit. It's not advanced enough, right? We can't just feed it a 0 in again and expect it to come back out as 0, because we've essentially just added a eternal loop in here. But we've got the right idea. I invite you to think for a moment, how can we augment our previous design to allow us to somehow reset the state of our memory, right? So in other words, this little loopy boy here, we need to figure out how to input something in order to allow us to reset this circuit, if you will. Unfortunately, the solution itself is not very like simple one-off, so we're going to go ahead and kind of walk through it together. And there's a spectacular video that I will share the link to of someone on the internet, and he describes the circuit just very well. Um, but here's the key: you can essentially perform this whole operation with a commonly used circuit known as a latch, right? That's the key there. A latch is what allows us to do this. And there are a few ways to build a latch, but today we're going to look at the most basic latch, and that is an SR latch. I'm throwing lots of terminology at you. This is where it kind of gets a little bit more advanced in terms of what's available to you in your toolbox in order to like build a latch, right? But in the interest of keeping this course kind of simple and focused, we're going to just be thinking about one particular latch design that we'll go ahead and implement within Minecraft. So specifically, we're going to think about a NOR SR latch, right? Um, and there are a few other latch designs that I'll probably be throwing up on the course website. Maybe, maybe not. I feel like it wasn't that useful last year. But if I get some demand for it, I can just throw them up. But you can look at them on your own time, because there are multiple ways to implement something like this. But again, keep in mind our requirements here, what we need, right? Um, and this circuit looks kind of ridiculous at the outset, right? But I promise it's not so bad. Um, so here's what we've got. This is a NOR SR latch, right? Um, give it a set and a reset state, right? And the real beauty of it is, if there's no input coming in, its state remains unchanged. That is, if nothing is coming in, right? Whatever's coming out of Q and Q bar is going to be unchanged, and that's kind of our neat little key here. So we can kind of talk about it. This one's a little harder to go over just because there's some overlap of signals, but we'll see if we can draw it out. This is my first time actually drawing it out on this thing, so we'll give it a try. So again, this is a NOR gate, right? And that's the opposite of the OR gate, the logical complement of the OR gate. So in other words, it will only be on here. Why don't I throw up a truth table for it? That might make it a little better. OR gate truth table. Just get it up on the screen here. Eh. All right. So, well, that's a little tough to kind of fit on there, but maybe this should be a little bit helpful. So you can see that for a NOR gate, right, the only time our input will be, our output will be 1, is if we don't have any inputs that are 1. So again, just wanted to give that as a refresher before we start kind of looking through this. But this is what a NOR gate does, right? Again, logical complement of the OR gate. I think we have some literature up for the first few weeks on that, just about logical complement and stuff. But it's the key of this whole latch, right? And I think it's neat and kind of poetic how the NOR gate, which is also functionally complete, kind of helps us out here in this essential circuit design. So let's go ahead and take a look at how we're going to leverage this NOR gate, right? So I'll kind of move this off to the side here. Hopefully that isn't. So again, just remember the nuances of it, right? I don't think there's space for me to keep it on the screen while I do this. So let's talk about this. Now, at the outset, and it's neat because you're going to find some weird stuff is going on with the circuit. At the outset, we have nothing coming in. So let's start with this gate. Let's start one step at a time, right? Nothing coming in, so we'll say, oh great. Okay, well I'll send some stuff this way, right? Because again, nothing's coming in, so this gate is on. So we're sending some stuff this way, coming in here. Boop. Now this fellow changes to off, right? And that's fine. And that kind of gives us this little bit here. So this is kind of our initial state, right? And our initial state can go either way, right? I want to emphasize that our initial state can go either way. And we're going to start off in Q bar, right? And we're going to call that our reset state. And the reason being is that this guy right here, I'm going to maybe highlight it. This fellow, Q, is what we're using to figure out whether our memory is saying 0 or 1, right? So that's kind of an important bit here to remember. This Q is how we're going to show how previously in the other slides that we had, that output, right? How we're going to decide whether we have 0 or 1. So it's neat stuff, and this is kind of the starting point for our circuit. So again, I hate when that happens. Okay, whatever. So here we've got nothing coming in from any of these, right? And that's fine. So we send in, well, we send nothing here. Start off with this circuit, right? And this comes in and says, okay, well, nothing's coming in here, so we'll go ahead and send a signal this way. Boop. And it comes out here, right? So again, this travels out, comes in here, and then when it comes in here, it turns this guy off. This guy says, oh, well, I'm getting one of my inputs as 1, right? Since I'm a NOR gate, now I'm not going to send anything this way. So in other words, this is the first singular particular state of the NOR SR latch. Now, does anybody want to stop me? Does anybody see any problems in that explanation here? Because there's one little thing that's kind of neat about the initial state of the circuit. So if anybody wants to throw it out, I'll give you a chance. But otherwise, no sweat. A little hint is like, how would you calculate the starting position of the circuit, right? Just go for it, throw it out there. Because I did make an arbitrary decision in here. It's kind of neat to think about. Exactly. Yes, Richard, you are absolutely right. I love the way you said it. I could consider which gate to build first, right? It's neat that way because when I interpret it here, I basically said, okay, let's start off with this gate, right? But if you start off interpreting at this gate with the OR gate, then you're going to find, and I encourage you to kind of do this in your head, you're going to find that if you start off interpreting with this gate, you're going to get the opposite state, right? So it's very neat how this works. It's kind of this weird circuit that hangs around in limbo. Um, and it's due mostly because of this cool loopy highway spaghetti business we have going on in the middle here. But it's exactly right. You have to consider which gate to build first. What's neat is that once you have build a circuit like this, we're going to want to establish one little thing in the contract, basically of running this thing, right? And that is, we don't want to send in R and S at the same time, right? And we'll talk a little bit about that later, but right now I just want to show you guys one cycle of this circuit. We can talk about that whole dilemma of building which gate first and business like that. So first things first, we have our latch like this, and we're going to call that the reset state, right? This reset state, that's where we are right now. Reason being, Q is off, and Q is who we're going to ask to see whether this memory is turned on or not. So suppose we wanted to turn this memory on, right? That is our first order of business. So suppose we want to set it, right? Well, let's go ahead and do that. Let us run it. So right now, our default state is sitting as it is, right? And now I'm saying, okay, well, I want to set Q to be on. It's just as easy as going to this S, right? Which is our set wire, right? Keep that in mind, our set wire. And we're going to say, okay, I want to send in a redstone signal to our set wire. So I go ahead and send in this, right? I'm turning this on. Now let's evaluate gate by gate. Over here, this is going to say, okay, well, I'm getting one input, so not going to send anything out here anymore. Not my problem. So he says, okay, cutting that off, right? And Q turns off. But now this turns off, and magically, now that we've gotten an input here, this guy is clear to report that he's been turned on. So now, since nothing is being fed to this gate right up here, he says, whoop, well, I am now producing energy, right? So Q gets turned on, and this goes all the way down here. And the beauty of it is, still nothing comes out here. Why? NOR gate, right? And here's the kicker, the best part, and I kind of want everybody to kind of know this. Now, when we've kind of sent one pulse through, right, and we turn off this input from S, the circuit stabilizes. Check it out. Now Q is on, and because of this NOR magic, nothing is coming out here. So our circuit is stabilized in this like state, right? And now this dot won't disappear. That's fine. That is Microsoft, whatever. The circuit is stabilized with Q being on. And that is pretty neat stuff. It's very exciting because this is exactly what we wanted to happen. We wanted to be able to send in a set, send input into both exactly. Exactly, Brian. That's the one problem with this circuit, right? So you will find the example, right before I answer Brian's question, you'll find that the example that I put forth here, if you send in a signal, and I encourage you again to kind of do it in your head, if you send a signal from the R now, while the circuit's in this state, it'll go ahead and flip right back over to making Q bar active and turning Q off. So in other words, when you are sending one of these fellows at a time, R or S, then you are having a perfect circuit, right? Your circuit will work exactly as intended and it is all good, right? Whenever you send something into R, it'll go ahead and reset it and turn Q to off, right? Just like I have here. And again, notice that the circuit stays in this state even when I remove all inputs coming in from R and S. So almost think of it like, boop, I'm sending like a little ping, right? Either to R or S while it's in a certain state to flip it back over, right? And just for the purpose of this exercise, suppose RQ is on, and then we mistakenly say, okay, I want you to set this fellow to on, right? You would get a little signal going boop right here. But the cool part is nothing will happen, right? If we're trying to set a circuit that's on to on, our circuit's going to say, oh yeah, no worries, my dude. I'm already set to on, so I'm not going to do anything for you. And again, so that's just a little signal. Again, if we send one from R right here, like boop, this little NOR gate will send out no signal and it'll go ahead and flip it back over to Q bar. So we've got a pretty cool thing going for us here, and it's great, it works, but it's also somewhat precarious because if we do end up sending energy to both of these at the same time, right, here's what'll happen. We'll kind of go through a little example here for the sake of answering Brian's question. Brian, this is excellent. This is kind of where your thought needs to be going for this one. So let's say we make a mistake, we make an oops, and we send in both these at the same time. Well, right now, first of all, we get nothing coming out, which is no bueno, right? So at the outset, that's no good. Um, so this particular case, when we send in both at the same time, nothing coming out of the gates, and that is kind of an oof, but useless, right? So that's fine. That's one case. Suppose we already have some good stuff going on. So suppose we have this gate is off, we send some stuff out here, Q bar is on, boop, 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 and this fellow, right? And that's kind of working as intended. That's all good. Suppose we instantly just go ahead and send in this stuff here, both at the same time, right? Well, this guy's not gonna have anything to report, so he'll turn off, right? Boop boop, and now that turns off. All gone. This is all gone. And this guy's gonna turn off. But the problem is here. Now we're no good. None of these fellows are on, right? Um, and we've basically just like yeeted our circuit. We've stopped it from working, right? So now that it's set like this, the only way to really kind of fix it is to turn off one of these first. Because if you turn both of these off at the same time, we might have a bit of an issue, right? And that being, so check it out. Now that we were always going to, basically what I'm trying to say is when we feed in both inputs at the same time, we're going to be stuck in this state, right? This is an important state to remember because once we're stuck in this state, it matters in which order you turn these off, right? Does that make sense to everybody? And this goes back to Richard's point, right? Richard made the point, which gate do you build first? Well, in this case, right, when we cut both of these off at the same time, we're basically building both at the same time. And that's not good for us because, I mean, essentially, it's going to go down to the circuit to who wins, right? So what I'm trying to say is that when you deactivate both these signals at the same time, you run into what we call, I mean, if you remember this from 216, undefined behavior, right? Because when this turns off, when these two turn off, it's kind of a free for all, right? The circuit's not designed to be in this state. So when these are off, it's kind of like a battle royale. These two are both like, oh, I'm good to go. So they send some stuff here, and this guy's like, oh no, I'm also sending some stuff. So they race to see who can reach the other gate first, right? Um, and usually one of them will win in some arbitrary fashion, but that's the key, right? One of them will win. We don't know which one. We don't know which one will reach this one first and stop this signal. You don't know if this one will reach this one first and stop that signal, but it's very clear that whoever reaches this OR gate, NOR gate first, they get to the finish line and they win, quote unquote, right? And that'll turn either Q or Q bar on. Which one? Who knows, right? um, Again, you might be wondering why can't we use this to build like a random number generator or stuff? That's like a key point of consideration. But think about this: on like a very low level, there are always imperfections that are going to make like one line maybe like somewhat kind of faster than the other, maybe some environmental factors that cause it, right? So again, not great for like random generation, but for the purpose of thinking about this circuit, right, you all need to understand that if you feed R and S at the same time and then you let go, right, eventually, as you will have to, it'll get screwed up. So a rule of thumb with this latch is we don't want to feed it both at the same time, because that leads to undefined behavior, right? Specifically when you go ahead and turn the connections off. Does anybody have any questions about that? I hope that was a like good enough explanation of the latch. I remember I had some trouble picking this up the first time, just because of the weird nature of the gates where they hang in limbo and stuff. And again, this diagram that I'm drawing is wrong. It should always be in a state like this. So it should always be in one of these two states. So feel free to ask questions. Let's talk a little bit about this because this is the real key of understanding this entire unit. And if not, I'll kind of get through the slides here. It looks like I am kind of low on time, somewhat unfortunate. So okay, I will just move on really quick. Um, okay, well we talked a little bit about this. And yes, so I do have a video that I'll link up from this guy named Ben Eater. Great guy, excellent explaining this stuff. If you didn't get what I said, you will get what he said. So we will throw that up eventually. And again, we're just talking a little bit more. So I kind of went over the example here, and I've got some neat diagrams here, right? This is how the circuit stabilizes with R equals 0 and S equals 0, right? You can see very clearly how that goes, right? Um, and again, we talked a little bit about the potential for infinite looping weirdness, right? Um, and again, I'm just going to kind of walk you through it. So suppose we have Q on and we want to reset it, right? Here's how we'll go step by step. First, this is set to 0. We feed in 1 here, right? First step. This gate says, oh boy, I'm not producing 1 anymore. So it'll produce a 0, right? And now that's 0. We're going to follow that 0 all the way down here to this gate, where this gate says, oh, I'm getting nothing in. Time to turn on. And it'll go ahead and turn on and stabilize just like this, right? So again, this is the one thing you need to remember from this entire week's presentation, just how this whole thing just happens, right? This process, step 1, step 2, step 3. Or yes, I labeled them wrong. That was 0, 1, 2, 3, but hopefully that kind of makes sense. So just go through that example, make sure you know that that is how that works. And that's basically what that is, right? So note that if we remove the 1 coming from R at this point, the output stays exactly the same. I'm going to kind of skip some of these slides because I kind of just went over this in my entire spiel, but if you're going to look back at the slides, got a great way of reminding you, right? And by the way, you can use NAND gates to build these latches. I particularly we don't want to go over them just because I feel like NOR gates are kind of easier to understand when you like think about the examples, but you can build an identical one with NAND gates. And of course, there are other types of latches in general. If you Google latches, right, you'll find a bunch more. But this is a one credit class. This is the one type of latch that we're going to be going over in depth. And you'll learn how to build a latch in Minecraft, and it'll be groovy. There is some stuff I did want to talk about flip flops and clocks, but maybe we can save that for next week. Just because Ashwath, I think we're like a project behind, right? Or
Yeah. So basically,
Mhm.
we still have time to finish all the projects. We're just like 1 week behind where I would have liked to been. So the current project that's being assigned is project 4, which has to deal with the multiplexers, demultiplexers, and basically finishing off your ALU. So it's assigned. I'd recommend you start kind of early because it's not hard to conceptually understand. It's just that you have to implement so much for your existing functions that it'll take a bit longer than the other projects. I gave like 2 videos at the bottom of the project spec that'll definitely help you with that. It basically walks you through how to do it. It's just from there, it's a matter of doing it. I'm going to release my project 3 solution today, so you can just add on to that. If your project 3 doesn't conform with like the same format as the tutorial that I gave. But yeah, other than that, expect the next couple projects to come like week after week after week with like no breaks because we do have to finish everything.
Yes. Solid. But yes, okay, so we'll save flip-flops and clocks for next time. I guess the key here was kind of understanding latches. Um, and I think if our schedule permits, we can just throw in some more. Um, yes, I can. So I did not upload the slides and video for the previous lecture. I will go ahead and get that up on the course website ASAP by tomorrow. So I just didn't upload them because of the midterm.
Project 4 is already out, Richard. I put it in the announcements channel a couple days ago.
Solid.
Unless I'm tripping. I'm
I think
fairly
you're good.
sure I
I
did.
think you're good. I think I saw it in there.
Okay.
Yeah. Yeah, it's right there. But yeah, well then I'll go ahead and kind of stop off there. That's good. And then maybe since we're a little bit off on lecture, perhaps I can work with Ashwat to put together like maybe like a supplementary session or something where we can kind of just help you out with projects. Ah, you are looking. Okay, so that is my mistake. I'll update the website real quick. So I didn't update it after the midterm, but we'll get to that. Just still working out midterm logistics. There's still some people who haven't taken it yet, so we're kind of just working out
Also,
situations with them. Oh,
also expect grades for everything so far coming by the end of the weekend. Like I know we haven't graded like any of the projects, but like I know for the project you can at least like run like slash test and know what your score is. So that's not too big of a deal, but expect Elms to be updated by the end of the weekend.
yep. There are no such thing as secret tests or anything, so what you see is what you get. Um, I think that should be all good. So again, hit us with questions and stuff. I don't think anybody should be behind in this class. I think you're all doing excellent from at first glance. So no worries. But I don't think anybody's fallen behind on the projects yet. But if you have, feel free to reach this right now. Right now is the time to reach out to us. Right? Don't reach out to us like a week before the deadline and say, hey, I haven't finished projects 5, 6, and 7, because that's not gonna work, right? So if you do feel that you're falling behind, just talk to us now, and maybe we can work out some schedule to get you moving along with this. We want everybody to do well and pass and be have a good grade in this class. It's not like we want you to fail. It's not like we're forced by the department to establish some distribution so that we get paid, right? No, that's not what the case is. So please, if you're struggling or if this is a tough semester, just reach out.
Yeah, we also realized that like this class's workload compared to some of the other sticks is a little bit greater in terms of the projects. So that's why we do things like the extra credit quizzes just to balance everything out.
Mhm. Definitely, just trying to keep it all good for everybody. Right on. All right. Well, that's all I had for the material for today. Glad that everybody could join us. I'm gonna go ahead and stop the recording.